central limit theorem. The central limit theorem is the reason when we are finding conditions, okay, for the sampling district, we go for a RIN. Remember, so our conditions are R equals a random sample. I is that independence 10n has to be less than capital N, our population size, and then N, our normal condition. So remember the independence condition, this allows us to use the standard deviation there. And then the normal condition, that allows us to get a z-score and then go ahead and get a p-value. Your sample size is greater than or equal to 30. And where that comes from is called the central limit theorem. So say, hey, we can draw an SRS of size N from any population. That population can be very skewed. Standard deviation, the CLT says when N is large enough, the sampling distribution of the sample mean is approximately normal. So you can imagine here, I have all these X bars plotted out, right? You could think about it this, if I would take, the population of people's ages in the United States. So my computer's a little slow, so be patient with me. Okay. Now, okay, if though I would say I take a random sample of at least 30 people, okay, at least 30 people, and I find their average age, and I did this for, so I had a true sampling distribution of a sample mean, right? Okay, the sampling distribution of the sample mean, that will be normal. Okay, that will be normal. Actually find a true sampling distribution of a sample mean? No model. And that's why we say, hey, N has to be greater than or equal to 30. Now, I do have this little activity that I did do with students pre-pandemic. I'm going to want to just take my word for it and stop right there and be done with the video. That's fine. But I'll just quickly go through it. So basically what I did, guys, is I said, hey, we're going to simulate. Sorry, you guys, my computer is acting up on me. Stay patient here for a second. I had them simulate this. So I had a computer program where I had them type this in, and this means I had a sample of size 5 right here. Okay, type this in 3 times into L1, and then they went ahead and they found the average, each one. So L1, L2, L3. So everyone in my class, right, they went and they found 3 averages from a population that was very skewed. And you can see that all of these X's right here, that represents each student had 3 X's up here. And we say, hey, this is still really skewed, right? Well, that makes sense, right? Because this simulation that I'm setting you up for, it does come from a skewed distribution. And so you can see that this sampling distribution right here that we have, it's not a true sampling distribution, but it is still skewed, right? And then what I did is I 10, okay? And they did it again 3 times. So they generated 3 different averages, okay? Sample size 10. Remember, the sample size 10 comes from a population that's very skewed. But when we found the average of the 10 people or units, whatever you want to think of it as, because it was a simulation, when we plotted it, look at here, it's getting a little more skewed, a little bit, but it's not as skewed as when we were up here. Again, my computer's going a little slow, so bear with me. Then we increased the sample size to 25. And you can see what happened here. Keeping in mind, remember, each one of these X's is not an individual observation. It is an average of 25 people or 25 units. Because again, a sampling distribution of a statistic, each one of these represents a statistic, an X bar or a P hat. In this case, it's an X bar. So this led us up to, hey, if we did 30, it's going to be really very simple. And that was the goal of showing why the central limit theorem works. If you have any questions, write it down, let me know, and you guys have an awesome day.